So we'll start with, we have seen regular functions on affine algebraic set, okay, affine algebraic variety or algebraic variety. But now we'll see that one can define for open subset. So okay, so this is all localization technique. So localization and Zariski topology. Yeah. So we will see how to define regular for regular function. See, if we have x, we know what are the regular functions on x. If x is a algebraic subset, algebraic variety, right? We know how do you define, but suppose you have an open subset. Suppose so, but on x you have a topology which is Zariski topology. But generally, when we do study topological space, you study functions on an open subset. So similar thing we want to do it here. So we need to define what is called the open regular functions on an open subset. So let let U be an open subset, and let suppose you have a function. Suppose you have a function, say suppose f is a polynomial function on x, but and such that and take a point such that f of x is not equal to 0, where x is a point. Let x be a point in U. If fx is not 0, then fx is not 0, then there exists suppose such that fx is not 0. Okay, let's not fix the point. Let's say that such that fx is not 0 for all x belongs to U. That means f is not 0 on the open subset U. Then I can define the function 1 by f, which is no longer a polynomial function. It's not no longer a function, but I can define U to k. So this is same as this k. So you take x to 1 by fx, and you allow such functions. So when you locally you want to allow such functions, because they are not polynomial, but they are inverse of a polynomial. So they are not bad in some sense. So you want to allow such functions, okay. So 1 by f is clearly defined on the set U, because f of x not equal to 0. So these also you want to include them as functions. So these are called regular functions on U, right? You take a polynomial f which is non-zero on U, and you take the inverse image. Then this is a function on U. This is called a regular function. So I will define more precisely what I mean. So these kind of functions. So once you allow this kind of function, then you can allow g by f kind of function. But g is a polynomial in kx, right? Because g is anyway it's a polynomial. 1 by f is defined. So g by f. So locally the regular functions on U looks like this, g by f, where f is non-zero on U. Okay, so I will make it more precise what I mean now. I will make a definition. So basically the functions, the regular. So this is the point. The regular functions on U looks like g by f, where g belongs to Gf Fg belongs to Kx such that F on U is not 0. And see, if you have two such functions G1 and F1, you can add them, just addition, because F1 and F2 both are non-zero on U, so F1, F2 will be non-zero on U, and similarly you can multiply such function. And of course, the constant function, the Gx is equal to, they are polynomial in constant polynomial, so they are also there. So in some sense, these regular functions form a K algebra, because you can add them, you can multiply them, and K is these are all K vector spaces, so it is a K algebra. But the only thing is that this need not be finitely generated K algebra. That is the only drawback. That this, see, in the affine variety case, if you take X to be affine variety, then Kx is always a finitely generated algebra. Kx is nothing but the regular functions on X. But here, if you take an open subset, you take the set of regular functions, this need not be a finitely generated K algebra. That's the only drawback. So you need to define something more general, that what are these? See, we know the affine varieties or algebraic variety, there is something one-to-one correspondence with finitely generated K algebra. But here, the regular functions are no longer finitely generated, so these are called quasi-affine. So you need to make new definition. Okay. So I'll make it more precise now. Yeah. So this is the motivation to do. So I'll define now. Okay. So more generally, so this is okay. More generally, a function h from U to K is called regular at a point. So this is again a local definition. When so it's a local definition at a point x belongs to U, you can f there exists f g in the, so U is an open subset. This is open subset in your variety X, algebraic variety. You can assume X to be as affine also. If there exists if there exists two polynomial Fg such that such that f of x is not 0 and h equal to g by f on Ux. And what is Ux? Ux is a small neighborhood open subset of U containing X. Once you have a topology on X, you know what are the open subsets and all. Okay, so you can talk about neighborhood of X. So that means an open subset containing U. So you say that it is regular at a point. So regular definition of regular, if you precisely, it's a very local definition. Regular at a point X in U, if there are polynomial f and g such that h, if you restrict to a small open subset around that point, it is of the form g by f. Now you say that h is a regular if at every point of U. So now you make it globalized. If it is regular at every point of U, then h is regular on U. So now you make it regular more if h is regular at every, h is called regular h is called regular if it is regular at every point, regular on U. at every point. Of U. So, what does it mean? That means for every x, that is for every x in U, there exists a open subset Ux. So, I call it x comma Ux because x contains Ux contains x, and polynomial like fx comma gx such that f of x comma x not 0. So, this fx gx are polynomial function. So, they are in kx. U is open subset here. Such that H restricted to this Ux looks like gx by fx, right. So, this is f of for all x in or fx of, if we don't have fx of y not 0 for all y in Ux. Yeah.
Ux is the complement of f of x equal to 0.
Ux is a open subset containing x.
It is not necessarily the complement where f
It you can take it to be intersection of d of fx where fx does not vanish intersect with x. But definition, when you say this Ux need not be the whole U. You will see when we define projective, the regular function on a projective variety, this definition will be useful. Okay. Okay. So, so this is a, so now the point is that if see this d of fx, these are of course open subset because this is nothing but x, if I call it x minus v of fx. See, fx is a function in kx. So, v of fx makes sense, the 0 set of fx. Now, the complement, this is the open subset in x. Now, this d of fx intersection u, this forms a basis because every point you can, there is a fx, right? Because after all this is a regular function. So, this forms a basis. So, remark d of fx forms a basis. Under Zariski topology. From the basis of, in fact, for the whole x, because you define d of fx to be open subset in x. So, this is a basis of x. So, now if you have a basis for x, now u is an open subset. If you intersect with u, that will form a basis for u. So, in some sense regular functions are useful because this gives you a basis of the topology, right. From a regular function you construct a, you take it to consider the open subset and they form a, but more interestingly this forms a structure sheaf. So, structure sheaf, so you define, so definition, let U be open subset in X and consider OX of U. This is a notation, okay. So, what is OX of U? OX of U are regular functions on U, F is regular. as I said that regular functions form a K algebra. So, you can add two regular functions f plus g, because locally you have to add. You take f, it locally looks like fx by gx. So, locally you can add, locally you can multiply. So, you can define like that. The f plus g locally looks like fx plus gx and fx and fg. So, f plus g, fg, these are all well defined. And this forms a K algebra. OXU is a K algebra. And only difficulty here is that you no longer get a finitely, it need not be finitely generated. So, this is a caution. OXU need not be finitely generated. And sometimes it is finitely generated, but there is no bijection with x. See, you remember that when you have a affine variety, another condition was that with k, the maximal ideal of kx, there should be a bijection. Sometimes it may be the regular function, may be the whole, it may be a finitely generated K algebra, but there is no bijection with the set x underlying variety. That is another point. That can also, I will give you an example, which I will leave it as exercise. You try. Okay. Okay. Before giving that example, let me tell that if so now you have taken as an open subset, right? So so as a in particular case, you can take u to be x, right? And exactly same way you define OX of x. That is regular functions on x, where x is a affine variety or x is a algebraic variety. So then the theorem proposition is kx. So for a algebraic variety x, the K algebra, the ring of regular functions, this is nothing but the coordinate ring, which is nothing but the way you have defined the functions morphisms from x to k. See, the advantage with this way of defining the morphism is that it is defined very locally, and that is what generally we do, right? When we define function on a topological space, we define very locally. Differentiation, continuity, these are very local definitions, and only when you define such locally it is useful, otherwise you cannot work with that. So, that is the reason why we define these regular functions, and then we say that whatever we defined previously, it coincides for when x is an algebraic variety.
So, what do you mean by structure shift?
So, this is called structure shift. See, structure, when you, so this algebraic variety gives a structure on this ring, it is a K algebra. It gives a structure like a complex structure. Complex, what is a complex vector space? It is a set with some structure. So, this is this will be useful. Later we will see that this shift, when I do shift theory, I will do little bit of shift theory, then we will see that these kind of these examples, these are most what is that? Is a the most it is some kind of canonical sheaf. If you have a algebraic variety, I can give you a sheaf which is this sheaf, which comes automatically to you, and everything is built on this. You take quotient, like whenever you see, when you see finitely generated module, finitely generated module is quotient of free module, but they are complicated objects. Similarly, you will see the covariant sheaf, these are quotient of this free sheaves or locally free sheaves more generally. So, this will play some power of this OX will play the role of free module when you do geometry. Okay. So, these are very useful object. Often we will see that whatever we study are either quotient or sum of these sheaves. Okay, so now, okay, not the function, this is in wrong notation. This is a coordinate ring. When when X is an algebraic variety. Obviously, the proof Kx is always inside Oxx, right? Because if you take just a polynomial function, they of course that is regular, there is no problem. After all, it is a polynomial function. But the converse, so the obvious, this is obvious. Converse, so suppose you take a function here, f in Oxx. So that means what? So that means for every x in x, there is a open subset Ux in x such that f restricted to Ux is given by some fx, right, where fx belongs to kx. That is the definition of regular function.
Divided by q. For the
Sorry,
we need case infinite gx by.
Yeah, assume all my definitions are for k algebraically closed field.
And also infinite.
Algebraically closed field, they are always infinite. Right. So locally, if around x, locally this f looks like it's a pair, right? Gx comma fx at x, locally at x. Right. Now the point is that f of x is not 0. Right, because it is regular. Now, if I consider this collection, this S, where x belongs to x, this is a subset of k of x, because fx are, after all, they are polynomials, right, but they do not have common 0, because if there is a common 0, then every function has to vanish at that point, but you know that there is a function fx which does not vanish at x. So, what does it mean? That means this, if you take the ideal generated by Hilbert-Knudsen search, see algebraic subset and the ideal, there is a one-to-one correspondence, and if there is no 0, common 0, that means the ideal will be unit ideal. So that means this collection fx generates the unit ideal, right? So this implies, let me see the notation. 1 is sum of Ax fx, where Ax also belongs to in Kx. Okay. So now this is identity, right? 1 is equal to summation f. I can multiply by f. Oxx is a ring, and these are all elements of the Oxx. Right hand side is also elements of Oxx, right? Because they are all regular functions. So I can multiply by f both sides. So then f is nothing but summation Ax fx f. But at a point x, f times fx is nothing but gx, because f restricted to ux is nothing but gx by fx at a point. So I can write this is nothing but summation x gx, right? Because fx times f is nothing but a polynomial gx. So, but this is a but ax is a polynomial function, right? Sorry, there is no x here. Ax is a polynomial, gx is also a polynomial.
So for like so this in that sum say there is f of x1 and f of x2. So now f times f of x1 is g of x1
Hmm.
and f times f of x2
Hmm.
is g of x2 in u of x2.
Hmm.
But if those two open sets are not intersecting,
They will intersect because I have taken X to be affine variety.
okay.
So, any two open set will always intersect. So, that is how you define. See locally I should have said this before. So, locally it looks like ux comma fx, right. And similar, so if you take ux1 and ux2, then if you define like this ux1 intersection ux2 fx1 plus fx2 and restrict to ux1 intersection ux2. But because open subset affine variety irreducible, so any two open subset will intersect. So, that's not an issue. Okay. So, now this will say that this will belongs to kx. So, this will say that oxx is in kx. So, the point is that the way you define regular functions locally, it is quotient of polynomials and they coincide with the regular function what you knew before, and that is the point. Okay. Now, the point is that so then the thing is that why did you do this? So, point is that why I did it, because affine varieties are not the all varieties. Open subsets of affine varieties, they are not affine. If open subsets of affine varieties are also, for example, you took you take this xf, which is vf complement. Vf complement in some x. Suppose f is some function in kx, or you can take x to be affine space. You take a polynomial, you take the complement of the 0 set of f, complement of the hypersurface, or that is a affine variety. By adding one variable, you can show that this is a affine variety. But that is not always, that this is open subset. This open subset is a affine variety, but not all open subset of affine varieties are open, are affine. For example, this, you take this an minus 0 or a2 minus an minus 0, you take this in an. N greater than equal to 2. This is an example, this is called Hartog's principle. I will leave it as exercise. So, you will see that Ox of u is same as k x1 x2 xn. But the close point of this, there is no one-to-one correspondence with the open subset u, because k is algebraically closed field. So, close points of is not close point, the maximal ideals of k x1 x2 xn, they corresponds to points of an. But in u there is one point less, so there is no bijection, right. So, that makes that this is not an affine, but this is called quasi-affine. So, new definition. So, this is not affine.
Can we say that affine open sets are only like complements of like zero sets of some polynomial?
This is zero set of polynomial, zero polynomial.
Like precise zero locus, like the x of f, that affine minus.
X of f will be always a affine variety.
That was the only affine.
No. Any union will be also affine. So, this, so I define a definition. Open subsets, quasi-affine can be affine, but not all quasi-affines are affine. Okay, so yeah, some quasi-affine, not all quasi-affines are affine. So, open subsets of affine varieties are quasi-affines. So, generally when we work with varieties, we always either assume that affine varieties are in general, if you include projective, either affine varieties or quasi-affine varieties or projective varieties or quasi-projective varieties. Okay. So, these four kind of varieties we deal with, they are easier to deal. Either it may be some complicated thing like quasi-affine union, quasi-projective. So it can, the varieties in general can be very complicated, but when we work with varieties, we deal with this kind of varieties. So, quasi-affine, affine, projective and quasi-projective. Okay. Okay. We will see more examples when we do projective varieties. We will see that irreducible, because we already know that Noetherian, we are in Noetherian, so anything is union of irreducible. So, enough to work with irreducible varieties. If it is not, then you intersect with the irreducible component and work with that. Yeah, component. Okay. So, now what I will introduce is another definition. So, the previous example says that there are quasi-affine varieties which are not affine. So, this is more general. Affines are quasi-affine, of course, but these are more general. And now you define regular functions on quasi-affine, like on any open subset, you define what are the regular functions. Once you know what are the regular functions, you know maps between two quasi-affine varieties. You say x to y, it is a morphism of quasi-affine if every regular function on y takes two regular functions on x, right. Just the way you define in the case of affine, that you say suppose x and y are quasi-affine, you say f is a morphism. If I take any regular function g from y to k, if I compose g composition f is a regular on x. Exactly same definition you follow. So, that makes the quasi-affine varieties a larger category, where objects are quasi-affine and morphisms are the quasi-affine morphism or morphism between quasi-affine varieties.
Will it be locally defined by polynomial?
Yes, yes, everything is through regular functions. So, regular functions are defined locally. So, whenever you define some functions, and that this is a point, starting point, you see that when you go to projective variety, you will see that there are not many functions, global functions. There are only local functions. A function, now you should not think a function is a map, is a global map from x to y. A function is a locally looks like a polynomial, locally looks like it is given by some function. So, that is how you should look at. When you see a map of manifold, a map of spheres, it is not not a global map, because there is no global map. Because there are no, see, point is that there are no global maps to the constant regular function. There are no global regular functions. That is the difficulty. So, whenever you have, but you want to define maps between, there are plenty of maps between such objects. So, how do you define it? To define a map, you do not need a global map. You need to define locally, and then you patch it in some way and define a function. That is how one should look at. So, this is true for nothing to do with algebraic geometry or algebraic variety. It is true for in differential geometry or even in topological spaces we do that. Same thing we are doing it.